it reads a value from the stack and then writes a value back out to that address. That one, %n, writes the number of bytes that would have been copied to the output so far. In other words, how much of a string we've generated so far, how many bytes there are on the string we've generated so far. So if a programmer wants to output or otherwise copy a user string, the simple error which they make is that they accidentally, instead of specifying the proper argument, a format string argument, they accidentally pass the user string directly as the format argument. In this sort of case, so that's just the printf user string versus the printf %s, which means print a string, user string. So that's a really simple error to make, and it will work perfectly. The code looks like it works fine, except when people start putting percentages in there, and that's why these bugs went undiscovered for so long. Because it looks like everything is fine. So if an attacker can control the format string, they can use %n to write arbitrary data. If they can control the string, they can control how many bytes have been written so far, then they can put %n and just start writing. They can randomly write a word to anywhere they like in memory. You can't normally have nulls in the data which you're writing or the addresses because it's a string again. And you need to have control over some stack values in order to be able to specify the target addresses, but those are almost always satisfied in every format string example. So once you've got, okay, so you can overwrite one word. It doesn't sound like that much, but there's lots you can do if you can overwrite one word. For example, you could overwrite the saved return pointer on the stack, but that's hard. Why would you? It's a bit, it has to be guessed, and there's not much point in bothering with that, when there are other things which you can overwrite which are at known locations. The most obvious example of that, and the one you may have heard about before, is GOT and PLT exploitation. The GOT and the PLT exist inside a program as stubs. When a program wants to call an external function, like a function in libc, what it actually does is jumps to its own little stub of printf, which is then overwritten with code to jump to the real printf. If you overwrite a PLT entry, then the next time it tries to call that function, instead it will jump to the address you specify, and you can redirect wherever you'd like to go. You can also do the same thing with function pointers anywhere in the program, add/exit pointers. The list is endless. If you can write data into the memory space of the target program, it's generally quite trivially exploitable. So just the example of the PLT, which I was talking about, if you have the code that's trying to execute printf, instead it does a jump to its local little PLT stub, which does the real jump into libc. Libc's printf. If instead you write over the printf stub and you point it but back to your stack user buffer, then that code will be executed the next time the function is called. Just want to quickly cover heap overrides too. These have been discussed extensively recently because a lot of overflows which are found now aren't overflows onto the stack, they're overflows across heap buffers. This is all very dry, but I really should cover it. Basically what happens is that when the system when a program wants to allocate large amounts of memory, it requests memory from the memory allocator, but the memory allocator can only get large amounts of address space from the system. It can't say, I need 4 bytes. It can't say, I need 8 bytes. Instead, the system wants to give large blocks of memory. So you have this user space memory allocator, which will take these big blocks, divide them up into smaller blocks as needed, and then hand it out. But of course you need to keep information about what's free, what chunks you have, what's in use, how big all the blocks are, all the rest of it. And what actually happens is that data is stored in line with the user's data. So there will be a bit of control data immediately before the allocated area, and then which is the metadata about the block. And actually, once the block is free, there is even some data stored inside the free block. And this metadata is used not simply to describe the block, which is next to it, but also to link the blocks together so that you can get from one block to the next one. And the key with heap overwrites is basically that if the metadata can be overwritten, you can subvert the logic of the memory allocator. Now, obviously, the memory allocator is trying to follow these blocks, and it's trying to correct the metadata. When a block gets freed, it tries to go to the other blocks and make sure that all of the metadata is consistent. But if you can manipulate the metadata just right, and there was a big speech about BSD heap smashing on this yesterday, and there are quite a number of papers on this. But if you can overwrite the metadata in a controllable way, then you can fool the heap implementation into believing that your little buffer is actually a block. And you can use the block to cause the heap allocator to overwrite arbitrary addresses with arbitrary values. And I don't want to go into a lot of detail about that one. There are better papers, and we really don't have enough time. And I think this is the final class which I'm going to be discussing, and that's integer evaluation problems. These ones have been getting a lot of interest recently because there are lots of them. These are really, in terms of future exploitation, this sort of stuff is going to be big. For example, OpenSSH, the recent OpenSSH hole was caused by an integer overflow, for example, the Sun XDR hole was caused by an integer overflow. There are lots of these still to be found, basically. Integer evaluation is actually such a simple problem, but it's so hard to spot and it's so hard to defensively program for because it's just not the way you think. And basically what it's based around is the idea that certain calculations result in answers which you wouldn't expect, and that's because C and C++ have certain heuristics or characteristics regarding their integer evaluation. In particular, numbers loop around. So if you take a signed value like int 2147483647, which is the maximum positive number you can store inside the integer, if you add 1 to it, you don't get an error of any sort. You end up with minus 2147483648. And that's non-obvious. You can also do other cool stuff. If you have an unsigned value, 4294967295, and if you add 1 to that, you get 0. An integer with six, so those are the sort of looping examples there. But there are also other ones which have been of a lot of interest lately. In particular, when you take a big value and you put it into a small value, you end up with non-intuitive results. So for example, an integer 65536, not a very big number, but that number isn't representable inside a short. So if you put that value into a short, you end up with 0. And the final example is that if you start multiplying numbers together, you can easily exceed the amount of easily exceed the value which can be stored inside the target data size. In which case, again, you get non-intuitive results. For example, this very large number times size of int, which is 4, you would expect it to be a very large number. It's not. It's 4. And so you can use this sort of thing to trick programs. So the common exploitation scenarios is that you can fool a program into allocating a much smaller amount of memory than it thought it needed. So basically what would happen is that you'd say, I'm going to give you 4 billion something of these things, and it would go, that's fine, and it would multiply that number by 4 or however much it needs for its data structures, and it will end up allocating 0, it will end up allocating 4 bytes, or it will end up allocating some ridiculously small number, and then it will copy in your data until you say, I'm done now. So you just can arbitrarily start overriding heap data. Basically, that's what happens. This is where heap overrides really happen. Once you've fooled it into believing that it's allocated the correct amount, then you just proceed to demolish it by overriding the heap. And the other common exploitation scenario is that you can fool the program into writing to memory which is outside the area which it thinks it's checked that you're writing into. So this would be the case where you say, okay, I want you to edit entry number 13, where there are 14 entries in the list. That's okay because the program will go, okay, is that number less than 14? That's okay, so that's within the bounds. But what if the number is negative? What if the number is negative 5073? That passes the less than check, but it happens to involve writing to memory way off somewhere somewhere elsewhere in memory. So you can sometimes end up overriding arbitrary data or interesting data. So okay, now that we've covered all that stuff, what's common about that? We just covered all these exploitation scenarios. What's of interest about that? The most common factors of exploitation, as you would have seen here, is that firstly you have a buffer and you can predict where it's going to be. So you can put data into that buffer and you can tell where it's going to be so that you can jump to it or execute the code inside that buffer. The second common factor is that the program uses vulnerable standard functions. That is, it uses functions which programmers typically use carelessly, and it uses them incorrectly and thus ends up with a vulnerability. And the third thing is that, okay, once the intruder has managed to execute their code or get the program to do something weird, that's fine because the OS will let them do whatever they could normally do, so that whatever the processor's privileges are, they can exploit as much as they like. So those are the three factors which make a host really, really soft and make point-click-kill exploits work. So now we'll actually talk about some technical protections, and we're going to talk about ways in which we can take away some of those exploitation factors and make it less likely to be exploited. Some of you may have heard of this one. It's called LibSafe. It's by Avaya Labs, but it's actually quite old now. You don't hear much about that anymore, but it's an interesting approach because what they do is they provide a library, a simple library, and all it does is it intercepts function calls. It intercepts calls to all of these vulnerable standard functions: string copy, string n copy, SDP copy, WCS copy, and all of that list. In particular, it also intercepts calls to VF, printf, and all the format string functions to try and fix them too. Excuse me. And what actually happens is that you take this library, you force it to be loaded into programs which you think may be vulnerable or that you want to protect, and you can do that via LD preload, or the etc. ld.so.preload file will cause the library to be loaded into every executable. And what actually happens is the library ends up being loaded before libc, which contains the real version of these functions. So it ends up getting control when these functions get called. And the replacement functions, instead of doing what they normally do, but before they call the original function, they verify bits about the data. In particular, what they do is that they check the destination locations for the copies and all the rest of it, and they make sure that it's impossible to override a stack frame. So the stack frame was the saved return address and the saved EDT. So they make sure that you can't override those things, and the idea is that if you can't override that, then you can't redirect execution, and thus you can't exploit the problem. So when they detect a stack frame override, they generate a trace, send a log to syslog, and the program's terminated. So basically what that looks like is that if we were looking at our earlier example, function B, which was being exploited, the copy would happen all the way up until the point where it was going to hit the stack frame, and so libsafe will just go, I don't think so, and will terminate the program as soon as it tries to write into that area. So execution isn't redirected that way. So yeah, now let's actually do some demos. Let's get some. Okay. So firstly, can people see that at all? I hope a little bit. Basically, the first things first, we need to have a basic idea of all that stuff we were talking about. We're talking about memory locations and predictability. Now, so if I look at this, I actually have a simple demo. Okay, I have a simple demo program which is designed to illustrate where stuff is in memory and how predictable it is. And if you take this particular executable, all of its code is between 804.83.AO and 804.9.894, and those addresses are absolute, so you know exactly what's going to be there. If you're trying to exploit a program, you will always know those addresses. They're given to you. The stack variable A is at 0xbFF404. On a standard system, the stack begins at C0000000 and goes up. So that's also a highly predictable location. A bit of guesswork maybe, but highly predictable. There's a small heap variable, which is actually allocated 804.9.8AO. You can see that it's allocated in the uninitialized data area immediately following the code inside the executable. And that's also an extremely predictable location. Small heap buffers are at predictable locations. That's 4K, that particular buffer. A large heap buffer, which is, I don't know how much it is, I think it's a meg or whatever. Anyway, a large heap variable C is instead up in this other area. Your standard heap has two main areas. One's for small blocks, which immediately follows the executable area, and one is for big blocks, which is inside what's called the memory mapped area. So you memory map anonymous pages, and those pages of memory are allocated from the memory map base, which is at 40000000. So the large heap variable is at this address, which isn't particularly predictable. Then we have a PLT entry. As we were talking about, you reach printf through a PLT entry. That's at an absolutely predictable location. You always know exactly where that's going to be. So if you do a jump to 8048.384, you call printf. But the actual real printf function is really in libc, which is loaded up above the memory map base. As you can see, it's just a memory map file. So just to show you more of that, if I cat the file proc self maps, what that does is it shows you the memory, all of the memory mapped area of a program. So you can see exactly what's loaded in your standard program, in this case cat. So cat's at 8048, that's where the actual executable itself is mapped. You've got the dynamic linker, which is mapped at the mem map base, F0000000, and then you've got libc and other memory map files, and the stack, which is down here. So most of this is extremely predictable. It's not a surprise that this is a soft target. If you're writing you can easily come up with very reliable exploits against a host like this. Okay, so now let's actually look at some exploitation of the common scenarios we were talking about. I just have some really simple vulnerable programs, deliberately vulnerable programs, which I would like to use to illustrate some of the various attack environments in which exploits work. They're not particularly complete. I haven't got examples of everything I've talked about, but I just want to give you an idea, and I want to show you how the technical protections can make these attacks not work. So looking at number one, it's really simple. All it does is it takes in a command line argument, it performs a bare string copy onto the stack, a name buffer of 1,000 bytes, and then it tries to print the name. So that's a trivially exploitable, your quintessential Stack Overflow. Vuln2.c. No, it's also a trivial Stack Overflow, but what you would have heard is that a lot of the more recent vulnerabilities have been in parsing code. It's where a big program like Apache or something has special functions to try and parse strings and do cool things with strings. Lately there's been a lot of work on finding vulnerabilities in those parsers. So what I wanted to point out was that it was quite common to encounter, like Apache will have its own version of string copy. It won't actually use libc string copy, or will it have its own parsing function. So here I've replaced the real string copy with just a fake string copy, or sorry, a replacement string copy. So again, this is completely exploitable, exactly like the other one was. Vuln3 is another example, except that in this case, the original user input is, instead of being stored inside the argument vector, it's actually stored inside a malloc chunk. And that's going to illustrate the fact that small malloc chunks are at predictable locations. You don't always have to be guessing the stack locations. You can just predict the other things too. Okay, and Vuln4. Okay, which is a format string vulnerability. Basically, it takes in a user's name, supposedly, then it does printf, and then passes the name which was entered as the format string argument to printf. So that's also exploitable. Let's take a look at that. I have a simple exploit for the first example, which was the bare string copy. Basically, all it does is it passes in a command line argument, which includes shellcode, followed by a predicted address on the stack. It predicts BFFFEEA8 is where the user buffer is going to be. Very predictable, it works. So I just get a shell, just drops a shell when you get it right. Exploit 2, it's exactly the same. All I have to do is predict a shell, all I have to do is predict another stack address. In fact, the same address works, it's just a replace string copy here, which is just as vulnerable. Exploit 3, this is the example of exploiting a heap buffer and understanding where the heap buffer is at a predictable location. So for those of you who can't see that, in this case, the return address which I predicted when I overflowed the stack is 804.982D, which is the small heap block area. So, I mean, it's quite possible to execute code in areas other than the stack, to find and execute code in areas other than the stack. And exploit 4 is the format string exploit, which again, all it does is it overrides a PLT entry, it overrides the printf PLT entry, and then it causes the next call to printf to instead jump back to the stack buffer in which the user's name is being stored. So this takes a while, sorry, but it will work shortly. Yeah, so there you go. Basically, it exploits that. What you're seeing there is all the format string because it actually does get printed out before the exploitation works, and then you just get a shot. So I mean, it's all good. But basically, we've just discussed a few of the attack vectors there. So let's see how libsafe goes against that. Libsafe is we're going to just do an LD preload of libsafe. Okay. Okay. And so now we'll try it against our first exploit. So now we've got libsafe being loaded. If I do an LDD of NLS, you can see that. Sorry, not sure whether you can see that, but you can see that now the first library loaded into every executable is libsafe. So libsafe is now supposedly keeping us safe. So our first trivial exploit, which was the one which tried to exploit the string copy overflow, the string copy shouldn't work anymore because we shouldn't be able to override the stack frame. So we should be safe. And indeed, that's exactly what happens. So if we try the first exploit, instead of succeeding, we get a message from libsafe which tells us where the crash happened and just gives us various diagnostic information and kills the program. So that vulnerability is no longer exploitable. Exploit 2, on the other hand, points out that the real weakness of libsafe, and that is that it can only intercept the functions which it knows about and understands. So it doesn't understand that all I have is a simple string copy replacement. So it won't protect this program at all. So exploit 2 works exactly like it previously did, and nothing happens. Exploit 3, on the other hand, it also uses the replacement string copy. So again, we're not saved there. And exploit 4 is an interesting example, because although libsafe is meant to keep you safe from format strings, what it actually does is it only protects stack frames. So when I override a PLT entry, it does nothing. It does nothing to save you. So exploit 4 works exactly as before. So there you go. There's no difference. Okay, so what are the strengths of libsafe? Libsafe is very easy to install. It has minimal impact on the system, basically. It's really a very trivial library. It does what it does it well. It doesn't do that much, but it does it well. It protects only the specified functions against only stack frame overrides, which really limits the vulnerability classes it keeps you safe from. That's its main weakness, effectively. And the format string code is very buggy. It's an illustration of the example that if you look at it's a very good illustration of the problem that if you're going to intercept other functions, you have to be able to predict how they're going to behave given any particular input and try and filter correctly. And it's the same problem with network RDSs. You never know whether that bit of traffic which is going past is actually going to cause something on the other side to happen that you didn't expect. So libsafe, for example, its format string code is buggy. It doesn't work. %1n will bypass all the checks, and it will work. So I mean, that's a bit of a problem with it. But having said that, libsafe, limited in scope, but its adverse impact is pretty much nothing. It's easy to install. Deploying it is a nil-sum equation. If it saves you from something, all good. If it doesn't, who cares? It's sort of like a trivial insurance policy. I can't say there's any reason why you wouldn't want to install and run libsafe, even though it may not save you. So now on to perhaps a little bit more well-known and further discussed examples. The open wall kernel patches have been discussed a lot. Solar Designer originally wrote these patches. Basically what they do is they modify the kernel, the Linux kernel, to try and prevent a certain selection of attacks. The most important feature, and the one which is talked about by pretty much everybody, is the fact that it introduces the fact that the stack is no longer in executable memory. So sure, you can jump there, that's fine, but the CPU will refuse to execute code in that region of memory, and it will just fault and die. So this is very similar to Solaris. I'm not sure whether those of you who run Solaris, there's a no exec user stack kernel parameter, which should be on by default, and it will also do exactly the same thing. And on HPUX, since 11i, there's the executable stack kernel parameter, which can also cause this to be the case on those two too. So yes, open will just prevents execution of code on the stack, and you get a segmentation. And you should get a segmentation violation. So what that actually looks like is that, let's say for example our format string override, where we tried to jump back into our stack buffer, you get the printf call, that would go fine. It would jump to your address which you've overwritten here in the PLT, and then when it tries to make the step back to the stack, it's game over. The CPU will just refuse to execute you. So at the time that was a massive breakthrough, but this has been around for a long time. In fact, so long that it's now part of some of the commercial Unixes. There are some problems with this. Some programs do attempt to execute code on the stack. Debuggers in particular, when they inject code into a process, they do so. GCC trampolines, a particularly weird feature of GCC, can cause this. And the kernel itself used to write code onto the stack and execute it onto Linux. It doesn't do so anymore, but that used to be a problem. However, most of these problems can actually be handled automatically by the patches, but there are some cases where programs won't work. They're very rare, in fact. And for those programs, you can just switch it off. You can switch this stuff off for individual programs. Okay, so fair enough. Okay, let's say, for example, you no longer had the ability. You had all your user buffers and they were all on the stack. What would you do then? There are still different avenues of attack rather than trying to execute your own code. The one which is really popular and common and people have talked about is returning into libc. And basically what that's all about is that there's this big library called libc which can do lots of stuff. It's got lots of code in it. So why bother injecting your own code when instead you can just modify the executable such that it will jump to those functions and execute them for you. So if you know what the version of the OS is on the remote machine and you know what version of libc they're running, then you can predict any location of any function you want to call. So what that would look like is if we had our buffer which we were overriding, instead of overriding it with our code which would normally be here, we just overwrite whatever we like. We override the return address with the system function, and we override the user string parameter instead with the pointer to the bin.sh string. So what actually happens is when function B tries to return, instead it'll jump to system with the argument of bin.sh and execute a shell. Hey, it's easier and better than writing your own shell code. So the OpenWorld kernel patches do go to some effort to try and stop that. What they do is they modify the mmap base, which I was talking about, so that libraries are mapped at addresses beginning with 0x00, which is the string terminator. So the idea is to try and prevent you being able to write past the function address and actually write the arguments, so that you can call functions still, but you can't write the arguments to the functions. But there are still heaps of other targets, and that's where return into code comes in. You still know where all of the code inside the executable is. You know where the PLT stubs are. You know where the program, you know where all the useful bits of the program's code itself are, and you can jump to them instead. Perhaps the most interesting example of that is that, for example, SU, the program SU, if you could exploit that, it actually has a block of code which all it does is set UID to root and execute a shell. So if you exploited that sort of program, then you just override the return address to call that function. We'll call the function. So yeah, let's actually take a quick look at this. Just have to be really quick. I've just rebooted my machine, and now I'm running the OpenWorld patches on this laptop. If it comes up. Unbelievable. I'll just have to reboot it again, so instead we'll go through some more of the slides in the meantime. Okay, so we'll have to delay the demo of the open wall patches for just a little bit, but let me just talk about the strengths of it in the meantime. The kernel patches have the feature that all of a sudden you can't execute code on the stack anymore, so that can make life a little bit more difficult for the attacker. And they have a minor CPU impact, and there are actually a number of other features of the open wall patches which are quite useful for security. On the other hand, they don't. While it changes some of this to make it a bit more difficult, it doesn't have any effect on the ability to execute code inside other buffers. Say, for example, heap buffers, static buffers, any other space where you can get your own input can still be executed. That's fine. And returning to code style attacks aren't prevented at all by OpenWall. And for those programs which do attempt to validly execute code on the stack, you have no option but to switch off the stack protections for those programs. So just let me. Okay, and from there we're going to go on to packs, but I'll just quickly show you the open wall stuff. Okay, so if we take a look at what our demo program used to look like, the output from our demo program, we could see that those were all the various locations. If we now run the demo program again, we can see that most of it's still predictable. The executable image is still at the same address. The stack variable is still at the same address. Heap variables are still at the same address, or slightly different, but that's explainable. But what has moved, for example, is the large heap variable. Because the memory map base moved to include 00 at the start, that's now moved to a very low address. And the printf function, the one in libc, is now also starting with 00. So you couldn't actually pass any arguments to it if you tried to do a return into libc style attack. And if we take a look at the memory maps, we can see that now instead of being cat at 8048000 being at the top of the list up here, it is instead now at the bottom, and everything else is mapped below it. So for example, you couldn't, if you had buffers up here, you couldn't use them to overwrite down to this stuff. In any case, now let's see how it actually goes against our exploits. See whether it stops any of them. The first one was a simple stack overflow. You'd expect this to be stopped since it tries to redirect code to the stack. So if I run it, instead of getting the shell, which I used to, I now get a segmentation fault. And if I look in the kernel logs, I can see that it logged a kernel message saying that a return onto the stack was attempted, and it failed. If I attempt exploit 2, which tries to use its own string copy and still exploit the same problem and jump back onto the stack, it also doesn't work. Because once again, code can't be executed on the stack anymore. And we get another error message in the log. Exploit 3, on the other hand, it uses a heap buffer. So it tries to execute code which is in a heap buffer. So that works. There's nothing to stop that in packs. So if you have other predictable addresses, you can proceed to, there's nothing to stop that in the open wall patches. So if you have another predictable address, you're all good, as long as it's not on the stack. An exploit 4, which is the format string, which tries to jump back into the stack area, it also won't work because again, the stack is no longer executable. So it doesn't work exactly as we expected. Okay. Okay. Anyway, we're just going to have to, do you guys have the books or anything? Because we're just going to have to follow a little bit outside the monitor because I need to use it to initialize the display on this machine. But basically, next we're going to move on to packs. Packs is much more recent. It is a relatively recent thing compared to the open wall patches. And I would describe it as effectively the nuclear weapon of technical protections. It is seriously good, very, very good, and it's renowned for being particularly difficult to break. So basically, what PAX does is instead of making just the stack instead of making just the stack non-executable, it actually also makes the stack, the heap, and the BSS static storage completely unexecutable. So at this point, where are you going to put code which you'd like to be executed? No, so this actually makes it pretty much impossible to execute attacks against, to execute your own code. So your only option is returning to existing code at that point. And even then, they've attempted to completely remove that possibility too. PAX has a feature called address space layout randomization. What actually happens is that it randomizes the addresses at which the stack and the heap are created. So all of a sudden, they're not predictable. But then it also goes ahead and randomizes the location of all of the libraries, making returning to libc style attacks extremely difficult, if not impossible, to achieve. So at that point, you're like, from an exploitation perspective, you're pretty much stuffed. Except for returning to code, perhaps the PLT, because it will be able to get to useful functions in libc. But PAX even has a new feature which can be used to randomize the address of the executable itself. The executable will actually exist in two spaces in memory. One of them isn't actually executable, one of them is. So the code will execute at this weird location where it doesn't expect to be. But then when it tries to jump to another location inside itself, it will instead cause a fault because that address is no longer executable. PAX goes, well, that's okay, and remaps the address back down into the new area. So that incurs a little bit of a compilation, of a performance impact. But at the same time, it makes these sort of exploits so hard it's not funny. There have been some papers for exploitation in very specific conditions, but this stuff is really very, very strong. So yeah, and in addition, because PAX is so incredibly powerful and it may cause, like some programs just won't survive. Actually, I just want to have a bit of an anecdote on this one. If you install this stuff and a program starts crashing and it isn't working anymore under most of these things, that doesn't actually mean that the technical protection is broken. In most cases, it actually means that the program you're running is really bad. If you know, like if you start running vulnerable software under this stuff, it will crash, and that's a good thing. That's the way it's meant to be. And if you start going, okay, well, you know, this version of Oracle is always crashing when my client does this or whatever, so therefore I should just, you know, disable PAX against this Oracle process. That's not the correct response. The correct response is, if you can, demand a fix from the vendor. You know, try and make vendors accountable, because the crash is being caused almost certainly but by the vulnerable program doing something stupid. It's actually showing you, it's behaving properly. It's just that people sometimes don't see it that way. So I just want to show you quickly PAX, because I can't really wax lyrical about it without showing you exactly what it looks like. So yeah, I've just rebooted my machine now. I'm running the PAX kernel modification, and I'm actually running it with full address space randomization. So even the executable bases won't work anymore. At this point, you know, everybody I know who's paranoid is running PAX. So if that's any you know, recommendation, that has to be it. So now that I'm running PAX on this machine, let's take a look at our demo program. Okay, the executable still appears to be at a predictable location, 80483AO, but if you actually try and use those addresses from an exploit, they won't work, because PAX will go, what are you doing trying to enter this location of the code from the stack or the heap or wherever else you're trying to redirect execution from? So the program will just die if you try and use those addresses. So they look like they're okay, but they're not. The stack variable is now at a completely random location, B9DB7C24. Very hard to predict. Heap variable B is still at a predictable location, because it's after where the executable in the executable uninitialized space. So that could be somewhat useful. The large heap variable is at a completely random location now, because the memmap base is randomized. The printf PLT stub is still there, but it's not usable, because again, if you try and jump to it, it'll go, I don't think so, not from there. And the real printf function is at this random location 2B406040. In fact, if I run it twice, you'll see that those addresses aren't even the same between executions. 2B406040. Instead, now it's 2D0D1D40. And the large heap variable, where it was at 2B, is now at 2D1B20. Oh, well, completely different addresses. As you can see, it just, from an attacker's perspective, all of the places which were predictable aren't predictable anymore. So I just actually want to show you one more thing about this because it's very freaky. If you take a look at proc self maps, which shows you the memory map again, you can see that things are just at really strange locations now. The dynamic linkers at 2.7. So this is the memory map base, which has been moved into randomly to 2.7. You've got the heap, which has been put at BA, like how that was decided, I can't imagine. And you have the second image. This is the actual real executing version of BingCat at 6804800, an unpredictable location. If I do it twice, it's now oh, that's strange, that's fine. Oh, well, there you go. You still won't be able to predict that remotely unless you're on the system. Anyway, so as you can see, it really makes life very difficult for an attacker. So let's take a look at our exploits. And I can tell you up front that none of them are going to work because everything which we're attempting is no longer the case. If we run exploit 1, it fails for 2 reasons, in fact. The first thing is it tries to guess the stack address, gets it wrong, because the stack's at a random location, so it's always going to fault. So it just goes off into some random location and it faults. If we take a look at oh no, there's no kernel, remember for that one. So if we try exploit 2, no, again, it fails because again, we predicted the location wrong, but even if we did predict the location right, we wouldn't be able to execute it anyway. There's just no way. Exploit 3, which is perhaps a little bit more interesting. Exploit 3 tries to use a heap buffer. You remember the small heap buffers we were talking about? But they're not executable anymore. So PAX has intercepted the task and prevented it executing. It's terminated the task, it's logged an error message, and it's even shown us the bytes which we were trying to execute, and that's the beginning of our NOP sled of our exploit. And it's just said no thank you. And finally, exploit 4, it's also not going to work because it tries to get back into a stack buffer. So once again, can't predict it and couldn't even execute it even if we could. So it doesn't work. Okay. So what are the strengths of PAX? Well, as I've said, it's a nuclear weapon of technical protections. It makes arbitrary execution flow and arbitrary code execution attacks extremely difficult. Very, very difficult. You start to have a very, very determined attacker to get past this stuff. If PAX has weaknesses, it's that the total address space layout randomization has significant performance impact, and that the executable remapping bit, which was one of the features I was really pointing out, is not particularly stable at this stage, but it only keeps getting better. And some programs validly try and execute generated code. They'll never work under PAX, but you can switch the features off on a program-by-program basis. Okay. So all of the attacks which I've described have been attacks against the program state. In this case, we've been modifying stack frames and all the rest of it. But you don't have to. You don't have to actually arbitrarily change execution flow. In most interesting bits of software, there may be other bits of the state which you could break and cause it to do strange things, like cause it to believe that you have credentials which you don't, or that you're authenticated when you're not. So against PAX and that sort of thing, these are pretty much the viable sort of attacks. And other than that, information leakage. If there are various ways which you can remotely get information from the target host, which will provide you some information about where things are, then they're going to become more and more valuable over time. So okay, so that's those are the generic protections we have time to cover. There are lots of other ones which may be worth consideration. Three of them, which are popular but I didn't mention, are StatGuard, FormatGuard, and ProPolice. All of them require you to recompile software. And I just don't think that makes them fair generic protections. Because if we're talking about commercial off-the-shelf software, you won't be able to do that. So they're useful, but limited to some degree. syscalltrack can monitor what programs are doing, and it could be useful host-based IDS. And systrace can limit what syscalls programs can call. So hopefully reduce what they can do once they get in. Stop them, arbitrarily overriding everything and make it a bit of a less soft underbelly. So we've talked about all of this stuff, and it all seems really good. Well, at least to me, I don't know about you, but it all seems really good and worthwhile deploying. Why aren't they out there in the world? Like, why aren't people actually using this stuff? And, I wish I knew the answer to this, because the world would be a much safer place for all of us if they were. But the reasons I hear is that people have a fear of the impact on their production systems. As I pointed out, if the software you're running is crashing under this stuff, most of this stuff is so stable and has been developed for so long that if it's crashing, there's something wrong with your software, and someday somebody may well be exploiting it. So, I guess you have your choice. You can choose to run buggy, unstable software, or and not run these things, or you can try and run a secure environment with some of these things. The unsupported software, these ones in particular, which can be a problem for some organizations. There are compatibility issues. The ones I've talked about, most of them only work on Linux except for libsafe, but there are lots of other technical protections which can be used elsewhere, like Solaris. But, there are disadvantages to them, fair enough, but in the vast majority of cases, these approaches will provide a strong immune system. They'll make your host hard to break into, which will make it orders of magnitude less likely to be the one which is broken into. So fair enough, okay, we discussed the technical protections, and they're all very hardcore and complex and all the rest of it, but there are other things we can do. There are other ways which we can just make ourselves different, so that even if they do manage to exploit the target bit of software, or they do manage to get in to pass some patch or something like that, we can still try and make it such that it's just not what they're expecting to exploit. People often say this stuff about security through obscurity, but I find it very hard to believe that somebody who's running Symbian OS on an ARM processor somewhere on the internet is going to have their Apache process exploited, because they're just so different. They're so different that it's outside the bounds of the attacker's understanding or interest to exploit those sort of environments. So that's the sort of thing which I'm talking about here. In terms of biodiversity, you know how we were talking about all these predictable locations, all of this stuff which we know what version of libc they're running, what version of the OS they're running, so we know where all the interesting things we want to play with are. It's all just so obvious. And with precompiled binary software, that's the way it is. If you're running Windows SP3, people know where the SE where various functions are going to be located, given your service pack and all the rest of it. So running commodity hardware and all this precompiled software makes it an extremely easy target. Point, click, kill exploits work because they can assume all of these things about the target. But if you're the only one who behaves differently, if you have a Solaris box which does something different, that makes you dramatically less interesting. Dramatically less interesting. So I'd like to talk a little bit about making yourself different. Recompiling applications you have source to will work really well there, particularly with the latest compiler, because all of a sudden things are different. The addresses are less guessable. But it's also actually possible to modify your execution environment, modify your operating system in general ways so that you're different. I'm going to discuss a few now, but there are so many different ideas which I thought of for this stuff that it's not funny. But a couple which I'm going to discuss will work quite well against the exploits we've been talking about. These approaches aren't designed to hold back the tide. They're not designed to hold back the army, but they are designed so that you're just different. The virus might not manage to infect you because of it. One thing we talked about is that libraries are at predictable addresses, so libc functions can be at predicted addresses, given a particular version of libc and a version of Linux or operating system. Because what actually happens is the libraries are mapped from the mmap base at 40000000, and then mapped upwards. So the libc, for example, is always at a known location. So the attacker can use that information in their exploit. But what we're talking about now is these slides are out of order. I'm sorry, but basically we can use a simple tool which is on the conference CD, which modifies the library and it adds extra space at the start of the library, padding it to any amount of space which we want. Although there is a README file on there about some bugs in dynamic linkers, but it explains it all in there. So basically we can move the library so that the functions are no longer where they're supposed to be. So the attacker can still determine it, but has to brute force it, and could have to crash the program how many times and all the rest of it, and may still never get it to work. So this can be a really good approach, and it can really kill, return into libc, or return into library style attacks. So what it looks like is this. Basically you have the library, system exec v fork, useful, interesting functions. We add padding space, all of a sudden they're not where they'd normally be, even though we're still running our stock Linux machine with our stock installation of Mandrake or whatever. Yeah, okay, so let me just show you a quick example of that. The other thing which I was going to talk about next, just while this machine is busy, I was going to talk about moving library bases, because as I said, libraries are loaded at a particular base address depending on where we are currently in the memory mapped area. We can also just load empty libraries in there. If we load empty libraries in there, then all of a sudden the memory map bases are different, but they can be much more easily brute force. So I'm not going to demonstrate that. That's a little bit obvious and a bit too easy to attack. So anyway, if I just do a really quick demo of this, it's not going to be anything special. If I just go into code, if I copy libc into this directory, right? Now what I'm going to do is I'm going to move libimage on libc. Okay, I'm just going to move it 1028 bytes. So all of a sudden every address is now 1028 bytes from where it used to be. In fact, what I can show you is if I run demo, okay, we can see that printf is at 40082D40, but now if I change ld library path to be the current directory, libc will now be loaded from this directory instead of in the standard directory. And now that was just it. Printf has now moved. So instead of being at 4008.2D40, it's now at 40083144. Everything continues exactly as normal. It's just you're the only person in the world with this libc. Okay. So if you just follow on in the notes, because I'm running out of time, so I'm just going to have to move quickly through these examples. One other option is that, as you would have seen through our exploits, we were trying to predict stack locations so that we could overwrite correct locations of stacks, jump back into a stack buffer, all the rest of it. But what we can do is, again, we can use a simple trivial library to move the stack. The stack doesn't have to be where it is. We can just randomly move it for random processes. We can just put it wherever we like. So one of the programs which is there's a library on the conference CD called libmovestack. That's exactly what it does. If you cause it to be preloaded into other executables, then it just moves the stack. So if I run demo, we can see that the stack variable A is at bff3e4. But if instead I export ld preload equals actually lib moves, okay. So if I ldd bin ls, right, now all of a sudden libmovestack is the first library loaded, and what it actually does is while it's initializing, it just moves the stack. So if I run demo again, we can see that instead of being at bff394, the stack variable A is now at a completely different location. In this case, it's B000F394, but you can randomly decide wherever you want to move it. And again, your machine will be the only machine which behaves like this. If we try the exploits, this will kill a lot of exploits. Exploit 1, which tries to predict a stack location, it fails and it's segmentation faults. Exploit 2 also tries to predict a stack location, so it also fails. Exploit 3 doesn't try and predict the stack location, it's got a heap location, so it does still succeed. And exploit 4, again, has to know a stack location, so it fails too. So, I mean, 3 out of 4 ain't that bad. So yeah, we move to stack base, and finally, this is a really interesting thing. Well, some of you might consider it to be really interesting, but basically what happens is that when you're performing a privileged operation inside an operating system, the way you do that, if you're going to read a file or write to a file, the operating system wants to make sure that you really have permission to do that and take care of you. So you actually just call a system call, and the system call is called by its number. So you say, okay, I want to do an exec, so I want to call system call 11, and these are the parameters. The system call numbers are usually fixed and known. So fork is 2 and exec VE is 11 in your standard Linux installation. But an application should never ever directly call syscalls. That's never required. You should never use the system call numbers directly, and libc wraps them up in functions. So you should only ever use the libc functions. libc and the kernel should be the only two programs which need to know this stuff. In a fully dynamically linked environment, say for example Solaris or Linux, that should mean you would never get, the userland code never needs the system call numbers. But on the other hand, shellcode does. Shellcode, in order to do anything, needs to know system call numbers. So normally they just hard code them because, well, they're fixed and constant on modern operating systems. But what we can do is we can use a kernel module, and what we'll do is we'll take two system calls and flip them. And then we'll just patch the libc, patch the C library so that it knows the real system call numbers now, which is also very trivial. So at that point, shellcode doesn't work, because it can't work out what the real system call numbers are, which it needs to call. But at the same time, the system functions exactly as it used to. There's no difference. So let's take a quick look at exactly what that looks like. Okay, so the first thing I need to do is I need to patch libc. I need to come up with a new libc. So I make a new one called modc.so.6. Right? Then I use fix syscall, which all it will do is it will find the system calls and it will flip to whichever I decide. So in this case I decided to flip 11 and 2, which is exec VE and fork. Okay, I do that. All it does is it disassembles libc, finds the calls to the system calls, patches them, fixes them. So if I take a look at one of the ones which it fixed, 0xb 770. Sorry. Okay, we can see that what's happened here is that this is the mob of the system call number into EAX. This used to be 2, it's now 11, and it's just been patched. And this is the actual call to the system call. If I try that on the real libc, you'll see what I mean. Yeah, as you can see, where there's 11, where there is 11 in our patched version, there's now 2. So all we have to do now is we take the patched version and we put it in our lib directory as modc.so.6. Okay, so now that's there, and now we have a kernel module, and all it does is every time somebody tries to open libc, instead it redirects them to modc. And this new modc now knows what the real system call numbers are. And you can no longer access the system calls with the other numbers. So if I just load that module, flip mod.o, okay, so that's it. And there's no really good way to demonstrate this except to show you the exploits. Because all of a sudden they just won't work. The hard-coded exploit numbers won't work. So there we go, and we just exploit 1, it tries to execute a shell, so that's not going to work, so it tries to call the exec system call. Oh god, did I do that? Did I fail? No, oh, that's right, sorry. That's anyway. Sudo. Okay, so now, okay, so there you go. So at this point, none of this stuff should work anymore. Okay, exploit 1 tries to execute a system call and it fails. Because all of a sudden, instead of calling what it thinks is exec_ve, isn't anymore, it's fork. So it's screwed, it doesn't work anymore. Exploit 2, again, tries to use known system calls, fails. Exploit 3, known system calls, fails. Exploit 4, known system calls, it also fails. Shellcode doesn't work in this sort of environment, and it makes it very difficult for an attacker to work out what the hell's going on, because it just doesn't behave like it normally would. So anyway, just to finish up as quickly as I can, I'm sorry that I'm running over time. In the future, there are other cool generic protections which are on the horizon, which are amazing. Program shepherding, for any of you who are interested in this stuff, please read that paper. It's amazing. It's basically you execute the program, you analyze its future code path, and you make sure that that's a valid code path. It works, and it's just incredible. If it ever is sufficiently high performance to be mainstream, it will really kill exploitation. There are also other efforts with program sandboxing. Subterfuge, Genus, and Systrace are the most obvious ones of those, and they can be quite useful too. Anyway, so that brings me to the end of my presentation. Does anybody have any questions or anything? I know we're out of time. No?
Yes. Do you know if there is some project for Windows on your account?
Yeah, absolutely. There are commercial products which do this. For example, Intercept provide a commercial product which does this sort of thing. There also was a rumoured port of PAX to Windows which used to exist. I don't know what's happened to it. I have been meaning to ask some of the people who are involved with the PAX project about it, but I'm not sure what's happened to it. I know that there is a version of PAX which exists. It may not be public for Windows. But hopefully we'll be seeing this stuff for Windows very, very soon. Any other questions? No? Okay, well thank you very much for listening.